Okay, so right now we're gonna solve this whole exercises. These are for this is a Miniklausur for ITE. This one is from 2023. As you can see, it says here 2023. So let's go ahead and solve these. The first one is which Wetterbereich can we have if we have a 6-bit number in Zweierkomplement? So let's remember something. Whenever we have a 0 at the beginning of any binary number, in this case, it means we have a positive, and when we have a 1, it means we have a negative. So in this case, right, if we have 6 bits, let's do a little quick table here. 32, 16, 8, 4, 2, and 1. If we do a quick table just like so, right? Oops. We just do a quick table. It looks kind of ugly, but doesn't matter. If we write any number, for example, 1, 1, 1, 1, 1, 1, in this case, we will have all these values summed up. So 32 plus 16 plus 8 plus 4 plus 2 plus 1. But in this case, we know that the first bit is not going to be a value. Rather, it's going to be a symbol. In this case, it's going to be a positive or negative. So if we have a 0, it means we have a positive. If we have a 1, it's a negative. So in this scenario, let's see what values we can get out of all of these. So let's see, 2, right? We can represent any values, any combination of values. We can say we have 4 bits, for example. We have 2 to the power of 4 number of values. So in this case, it will be 1, 2, 3, 4. I think it's 8. 2 times 2 is 4. 2 times 2 is 8. Oh no, it's going to be 16 values. So in this case, we have 16 different values. Now, remembering this logic, if we have 6 bits, right? So 2 to the power of 6, right, is going to give us basically, let me just do the calculator real quick. Because I don't want to do the math in my head right now. 2 to the power of 6 is going to be 64, right? However, we know that 1 bit is used for the sign. So this one is used for the sign. So we're going to do -1, right? So in this case, we have to also do -1, and I'll explain why. So 2 to the power of 5, right, -1 is going to give us 31. That's going to be for the positive numbers. And this includes 0 up to 31. That's why we remove a 1, because we're including the 0 here. And then for the negative numbers, it's going to be the same thing, except without the -1. So it's going to be -32. Meaning, after doing all of this, that we have a total amount of -32 to 31. That is a range. This one is telling us how to create a number n with a polyaddition silent system as a mathematical formula. If you remember properly, it's just the sum of all the values. For example, 103, right? How do you create this number? Well, you multiply, right? 1 times 10 to the power of 2 plus 0 times 10 to the power of 1 plus 3 times 10 power of 0. In this case, it will be 10 times 10 is 100. 100 times 1 is 100. Plus, this is going to be 0 plus 3. And as you can see, we have 103. So in the sense, it's always going to simply be this. So it's going to be the sum, right, to n, I begins at 0, where we have ai, right, times the base, which is going to be b, I to the power of I. This is going to be, simply put, our solution. We want to convert this number in hexadecimal, and we want to convert this into the BCD. So 42, we can always do it, obviously, by dividing by dividing it. But in this case, I'm just gonna do the binary conversion, which is way quicker for me in this sense. So we do 1, 2, 4, 8, 16, and 32. We're gonna do this, right? And let's see. In this case, 42, what would add for 42? So let's add first 1, 1, and 1. This is gonna be 42 in decimal, meaning we can now convert to hexadecimal. So hexadecimal, remember, we divide by 4. Well, we have 4 different things, so it's gonna be like this. Oh damn it, let me just erase this. This is not nice in this case, and we can duplicate it. All right. So in this case, we start from right to left. So we have, in this case, 4, and then just this. So we have 2 other zeros here. So 0, 1, 0, 1, and then we have 0, 0, 1, 0. In this case, this is going to turn out to be 2, and this is going to be, let's see, 2, 10, this is going to be A. So A. Therefore, this will be 2A, right? So we can write 42 in decimal is equal to 2A in hexadecimal. Now let's check for the BCD. This is really simple. It's just 4 and 2. So we know that 4 and 2 is going to be 8, 4, 2, and 1. 4 is going to be 1, 0, 0, 0. And 2 is going to be 0, 0, 1, 0. Therefore, the BCD is going to be, therefore, we can say that 42 decimal is equal to 0, 0, 100, 0, 0, 10, and this is going to be BCD. So that's our solution right here. Let me just do this for the solutions, right? In this case, this is this, and this is this. So now we have D. D, they're asking us, we have to create this in binary, and we have to add them up also with binary. So it's really quite simple. So we know that 12, for example, 12 is simply going to be put, let's just do this real quick. We take 12. So let's see, 8, 4, 2, 1, right? 12 is going to be just 1, 1, 0, 0. It's going to be 12. And 7 is simply put 1, 1, 1. This is going to be 7, right? So we keep this in our back pocket. We're going to need them later. Now we need 0.5. 0.5. So we take our calculator here, and we do 0.5 times 2. This is going to be 1. So 0.5 times 2 is going to be 1. And this is going to be just 0, 0. So that's it. So 12.5, simply put, is going to be to 1100.1. That's it. And now let's do 2625. All right. 0.625 times 2 is going to be 1.25. So 1.25 times 2 is going to be 0.5 times 2 is going to be 0.5 times 2. 0.5 times 2 is going to be 1, 0, 0. So that's going to be 101 from top to bottom. So we're going to have 7.625 is going to be equal to 111.101. That's it. So remember, we count from top to bottom like this. Now we're going to add these two guys up. So let's duplicate them, add them up. Not that difficult. So what we do is, actually, I'll just rewrite them so we have a proper spacing here. Oops. 0, 1, 1, 1.101, and then 1, 1, 1, oops, 1, 1, 0, 0.1, and we add them up, right? So it's going to be 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0. So that's our solution right here. That's our solution. Okay. Now they're asking us to do the subtraction of these. So we start this by doing the second complement of this. It's really easy. So we just take 1, 0, 1, 1, 0. Oops, I'm getting confused. So this is 1. Let's just write it right next to it. So 1, 0, 1, 1, 0, 1, 0. And then we add 1. So it's going to be the same number, just with a 1 at the end. This is going to be our second complement. And we're going to add this up to this guy. So we're going to have, simply put, just like that. 0, 0, 1, 0, 1, 1, 0. So we add them up. 1, 0, 1, 0, 1, 1, 1, 1, 1. That's our value. That's our end value. And they want this to be in decimal system, right? So in this case, we have to look at this. We have to look at this number. And we're going to see that this value, we have to, again, see the value. So in this case, we know for a fact that this value is bigger than this one, right? So we know that this value is bigger than that one. So yeah, this one is bigger than this one. Meaning this one's bigger, meaning our result will be negative. As you can see, we have a negative thing here. So we know for a fact it's negative, so we're going to write a negative. And we're simply going to rewrite our solution, so it's a positive, a bedrag, so to speak. So we just do the opposite. So we're going to do the complement of this, the second complement of this, so to speak. So it's going to be 0, 1, 1, 1, 0, 0, 0, add a 1, 1, 1, 1, 1, 0, 0, 0, 0, and 1, 1, 1, 1, and 8, 4, 2, 1, 1, 1, 1, 1. This is going to be 1 plus 2, 1 plus 2 plus 4 plus 8 is going to be 15. So this is going to be 15. So our last value is going to be 15 in decimal. Minus 15 in decimal. This is a D. Right? So we can just, oops, we can just write this as so. Given C, the formula and the formula and the angibt. Okay, so this one is basically just asking us the formula for the IEE 754 Gleitkommazahl als Dezimalzahl. So we're converting the Gleitkommazahl into a decimal. It's really easy. We have to remember that it's going to be -1 Vorzeichen. I think it was times 1 plus m times 2 to the exponent. And we have to remember that the Vorzeichen, it's just the sign, first bit, is going to be the first bit. M is given as the character, no, the mantisse. Let me remember. Yeah, the mantisse divided by the length, where it is mantisse. This is the length of bits of mantisse. And then we have, that's basically for M. Now, for E, is character minus BS. And we know that the character is going to be just simply put binary of exponent. And the BS is going to be equal to, basically simply put, the amount, well, the binary of length of character. And we can remember this from our blatt. Let me just remember where it was, just so we can like review what we're looking here. It's blatt 4. So we look at blatt 4, we can see that let's look at here, that the bias, right, it's going to be, oh, the bias is binary. Oh, I forgot, this is not it. This is not this. The bias is going to be 2, and then length of the character, -1, and then -1. So simply put, this is our bias, which is over here. The character, again, is a binary of the exponent, which is this guy. The Stellen, which is this, and then Mantisse is given by this, right? And so our last formula is this, right? -1 / 1 plus m, 2 times, times 2 to the power of e. And that's how you get it. Okay. So the Blocksicherung. Okay, so we have all of these. So let's write this in a Blocksicherung approach. A4, A3, A2, A1, oops. B7, B6, B5, B4, B3, B2, B1, C7, C6, C5, C4, C3, C2, C1. And we're going to have, so to speak, just like that. So they're asking us how many proof bits do we need. Oops, why is it not writing? I don't know. How many proof bits do we need? It's not writing here for some reason. Just reset our guy here. Yeah, there we go. We want the proof bits that are needed, right? When we have the Prüfsummen und Spalten. So, in this case, we need 1 proof bit here, another one here, another one here. So it's going to include 3, right? 3 proof bits. And then we have 1, 2, 3, 4, 5, 6, 7. So we're gonna need 7 proof bits. Therefore, we need 10 proof bits. And that's simply the solution. In this case, this is the solution. Yeah. Which Hamming distance has the Kodierung of the vicinity Daten. So the Hamming distance, that one is interesting. If I remember, we'll have to look at my notebook here. Hold on. This is my notebook. Okay. So in this case, we have, we have 8 bits, right? 8 bits here. And so each message, so in this case, we have a length of 8 bits. So, in this case, okay, so yeah, I forgot a single piece of information here. We have to remember this: beliebige Einzelbitfehler korrigiert werden können, right? So in this case, we want to only find we need a Hamming distance so we can find a single bit error, and we know that e to fix, right, is given by d minus 1 over 2. In this case, e fix is going to be equal to 1, so d minus 1 over 2, d is going to be equal to 3, right? So it means the Hamming distance hd min has to be 3. That's a solution. And that's pretty much it. That's it. Now let's see. Wodurch erkennt der Empfänger einen Fehler und wie würde ein Fehler korrigiert werden? So simply put, basically we just have to see the column and the row where the proof bit is not correct. So for example, let's say we have the 3 messages. This is, we need 8 bits. Was it 8 bits? Yeah, we need 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 1, 2, 3. Perfect. 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. That's pretty much what we need. So in this case, let's say we have, let's start with the rows. So the rows, sorry, the columns. In this case, we have 0, and in this case, we're gonna have also 0. 1, let's put 1, so it's even. And then here, let's do a little error, right? Let's write 1 here. Do 1, this is gonna be 1, this is gonna be 1, 1. What I'm basically doing here is we want to have an even amount of ones when we count the whole row. So in this case, I added a single error here, so we can explain how it works. So basically here we have 3 zeros and 1 1, which is an odd number, which will make an error, in this case in your parity bits. And we check for the same thing here. 1, 2, 3, 4, 5, 6. So we're gonna add 0 here. Actually, let me think. I'll just add a 1 here. This is 1, 2, 3, 4. So this is 0. And we have 1, 2, 3, 4, 5. So we add a 1. So we have 6. So in this case, we can see that the error will track down. Oh, we have an error here because the amount of ones is uneven. And then here as well, we will find an error. So if we track it down, right, this is the error. So that's how it works. What happens when a single bit error? There's an error with a single bit error. Well, simply put, the global bit will also like catch an error, so to speak. The system will still work. Like, yeah, it'll still work. It still works. Still works as we have as this system detects single bit errors. So we continue. Then we have E. Nope. It can lead to ambiguous errors. Because look, we have 0, 1, 0, 1, which just has even parity. And then we do the error. And let's say all of them are correct. That's even parity still. And we can say that even if parity is still even for all columns, right? For simply put, we can say even parity. Just look at this real quick. In this case, even if we see that it's an even parity, we cannot know which column caused the issue. We can't narrow down the faulty column. Is there a Blocksicherungsverfahren that uses less proof bits than A? In this case, there is. It's the, what's it called? It was a something. code. I've totally forgot the name of it, but I do remember we have it here. It was in Blatt 2. It's called, it's right here. How was it called? I don't remember how it's called. It's this little guy here. Let me just see the actual Übung. Because I don't remember the name of it. It was the Hamming code. The Hamming code, of course, it was the Hamming code. So in this case, oops, where am I going? The Hamming code. The Hamming code. And the Hamming code uses the following formula: LD K, well, LD whatever, so message plus 1, right? So in this case, if we have 4 variables or whatever, we'll use that. So in this case, LD 8 is 8 bits, right? LD plus 1 will give us 2 to the power, well, LD is going to give us 3, so 3 plus 1 is going to be 4 bits. In comparison to the other one that we had to take about, well, per message we needed, let's see, 1 and then 2, no, 1 and, sorry, no, in comparison to, no, it was 24 in this case, we need 24. Yeah, totally dumb mistake here. So 24 plus 1, it'll be 24 plus 1 is going to be 1, 5 plus 1, which is going to be 6, in comparison to the other one that uses, well, 11, right? Comparison Block-Sicherung is equals 11 proof bits, right? Yeah. So what else? Now this one is pretty easy. It gives us fluency, das Symmetriediagramm für die Funktion, blah, blah, blah. So they want us to find the conjunctive minimal form and the disjunctive minimal form. So it's really easy. We start off by finding the key NFs, so the normal forms. So let's do the D and F, right? So in this case, we're going to do D and F, which is going to be DCBA. In this case, how many 1s do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to write 9 different DCBAs. Quite a lot of work, actually. Okay, boop. DCBA. We erase this. Okay. So DCBA. In this case, we focus on the first one, which is going to be this. We start here. So it's going to be not A, C, and D. Not A, C, and D. So we erase this one. Then we have not B and not D. Not B, not D. Then not A and not D. Right. Then we have not D. Then we have not A and not C. Not A, not C. Then we have not C. Not C. Then we have not B. Not B. Then we have not A. And then we have all of them together. Then we're going to do the DNF, so to speak, of the don't cares, because we don't want to work with the zeros. It's a lot of zeros. So we just focus on these guys. So let's close these guys too. So in this case, we want to focus on this one. It's gonna be DCBA. All of them are gonna be, yeah, DCBA. They're all gonna be canceled out. And then we have DCBA, just CBA. And then what did we say? It says CBA. Yeah, CBA. So we cancel these out. And now we put them in the table, right? So not D. This is gonna be not D. This is gonna be not B, not B, not A, and not C, because I like to look at everything. So not D, not C, and then B, not A. I think that's the one. So not D. Okay, let's check it out. Not D, not C, B, yeah, and not A. So that's correct. So we can close this up. Now let's continue with not D and C, not D and C, and then it's gonna be, well, not D, and then C is around this area. Then we want B, not B, so it has to be around this area. But we want A, so it's gonna be around here. So check it out, D, C, B, and A. Let's check it out, D, yeah, C, yeah, B, A. So that's another one that we say. I'll just continue doing this on. I will not write down everything, but I'll do it real quick. D, C, but B, but not A. D, C, D, C, B, but not A. Perfect. We want this one, not D, but CBA, not D, but CBA, that's another one. Not D, but CBA. Oops. Close this. D, not C, D, not C, but B, but not A. I think that's the one. It's A, B, D, C, it's D, D, yeah, C, yeah, B, yeah, A, yeah, perfect. Let me close this up. And we have D, not C, D, not C. Then we have B, we want A. D, not C, B, and A, perfect. Now we do D, C, not B, D, C, not B, okay, and A, D, C, not B, and A, okay. That checks out. DC, B, DCB, so this area, but A, oops, that's gonna be D, C, B, but not A, perfect. And then the last one, DCBA, DCBA, perfect. And now we're gonna do the not DCBA, DCB. I think this is the one. C, oops, no it's not. It should be this one. C, no. Is it this one then? C, A. Yep. That sure seems like it. So we close this up. And then the other one is here. So we close this up. So the rest are zeros basically. So we want the conjunctive manifold. The conjunctive manifold is basically with the zeros. So let's do that real quick. So the zeros are gonna have, basically, simply put, we can take these, right? And I'm pretty sure we have to take this, and then we can take maybe these two like so. And this is going to turn out to be no conjunctive monochrome. A die. Let's do the red one first. A is not there anymore. B stays. C stays. C stays. B C. C stays. B and D also dies. So in this case, it's conjunctive monochrome. So remember, how to add them like this. Okay. Then we have another one, which is gonna be the orange one. It's gonna be A, B dies, plus C, C stays, and plus D. Yeah. Then we have the last one, which is gonna be the purple one. It's gonna be A negative. Then we have B as well. C. Oops. C positive and D dies, yeah. So that's your conjunctive monochrome basically. Just adjust it for, oops, I missed negative here. Now we'll do the last one, which is going to be this guy. So, oops, totally forgot about this guy. We have 4 here. Then we have, let me check another color here. Whatever, dude. I can't be bothered. Then we have 4 here, right? Then we have 4 here. And then we have 2 and 2 here. Oops, no, hold on. We can do this actually. And then we cover everything, huh? And then we can actually cover this guy as well. Way smarter. So in this case, we're gonna have, I'm gonna write it down real quick so I'll have not much more time. But simply put, oops, it's gonna be, oh, this is conjunctive monochrome. So we have AC plus BT plus A, oops, B. So we put it here. That's perfect. A can basically is prime implicants. Prime implicants that cover a unique cell or a min term, also known as essential prime implicants. Always need to be present in any minimal form. So the conjunctive monochrome, we want to give all these guys. So in this case, it would be these. The canon. The canon are the ones that don't overlap. Yeah, basically, simply put. So it's basically these. Because remember that we can have more items in our minimal form. For example, in minimal form, we could include, for example, let me just erase this guy, so we can have a more clear vision of what we're talking about here. We could also include, for example, in our minimal form, hell, I don't know. We could also include this, right? Or we could also include, oh, yeah, I totally forgot. For example, we can also include, another one that we can include is this one, right? So it's like, it depends on each one. But that's it.